Hello everyone, I hope you're all doing well. We're going to be looking at the work energy concept or the work energy theorem today. Okay, so work energy theorem or the concept of work and energy. Okay, so let me get this started off by looking at a particle which is traveling along some kind of an arbitrary path. Okay, so here is a particle that is traveling along an arbitrary path. Okay, so I always try to get this done, but sometimes it blows up on me. All right, so this is point one. Let's say that position one of the particle. This is the particle at some position two. Okay, and then I'm looking at the position of the particle at some arbitrary point in time here. Okay, let's say that in a time interval dt, let's say that this particle moves from this position all the way to some position that is slightly away from where it is. Okay, so let's say that it moves from there to there. Okay, so this is the position of the particle as it travels from one point in time to another over a time interval dt. Okay, then I say, okay, at any point in time I can say the net force acting on the particle, okay, is the following. Okay, so let's say that, okay, here is the force that is acting on the particle. Okay, so this I'm going to call as the force F. Okay, and F is the net force on the particle. Okay, so F is the net external force on the particle. Okay, and the particle is traveling along some arbitrary path of the particle. All right, and so what I'm going to do, I'll get rid of this small term. Well, I guess I'll keep this anyways. So what I'm going to do is I'm now going to define a term called as infinitesimal work. Okay, so we shall now define. So we shall define infinitesimal work done du by the net external force F on the particle as the particle is displaced by an amount dr in a time dt. Okay, this is infinitesimal time. Okay, and so here you see the particle getting displaced by an amount dr, and what I'm going to do is I'm going to draw the unit normal and tangential vectors. So this is going to be the direction of the tangential unit vector. Let me just make sure that it's drawn that way. So this is the tangential unit vector, so which we will call as E suffix t, and then of course perpendicular to that, pointing in the concave side of the trajectory, is going to be E suffix n. And let me say that this particle here, let's say is a little closer to. Okay, so this is the particle, and you will see that the amount by which this particle is moved, which I'm going to call as dr. Okay, so this is the amount by which the particle has moved, and I'm going to call that as dr. This is the displacement of the particle in that very small time interval. Okay, and what I'm going to do further is I'm going to take this force and split it into a component along the normal direction. Okay, so this is going to be a component F suffix n or Fen, and then this is a component in the tangential direction, so I'm just going to call it as F suffix t. Okay, so this is the component of that force in that particular direction, which means that this net external force can be written as some magnitude in the tangential direction and some magnitude in the normal direction. And you will also notice that this displacement vector dr can be written as some distance traveled in the tangential direction. Okay, this is something that we know from basic particle kinematics. Okay, so now I'm going to define the infinitesimal work done by the, okay, so important terms that I'm going to talk about. So this is the work done by the force, okay, by the net external force, not just any force, on the particle. Okay, so this is the definition of what I'm calling as infinitesimal work done. Okay, and this is called as du. Okay, so du, or capital U, I'm sorry, so du is defined as f dotted with dr, or du is the dot product of the net external force on the particle and the displacement vector and the displacement vector. Okay, so this is the dot product, and let's then we can go and further say that, okay, what if I'm not interested only in this infinitesimal work done? So this is infinitesimal work done. Okay, infinitesimal work done. Okay, but what if I'm interested in work done over the entire path from point 1 to point 2? This is nothing but, if I take this think of this path as split into a large number of smaller tiny pieces, then the net work done as I go from point 1 to point 2 is nothing but the integral of all the infinitesimal work done. Okay, so which means that the net work done, okay, by the force, by the net external force on the particle as it goes from position 1 to 2, okay, is the integral of all the infinitesimal work done along the path. Okay, which means that I can say u1 2. Okay, so this is the work done as I go from position 1 to position 2. So this is going to be integral from position 1 to position 2 du. Okay, or by definition du is f dotted with dr, so this is going to be from integral 1 to 2 f dotted with dr. Okay, but we also know that the force F, as you know from here, the force F is Ft et and Fn en, and then the displacement vector is also known to us. So I'm going to bring this guy here, so we know these. Okay, which means that if I do the substitution, u12 is going to be integral from 1 to 2 Ft et Fn en dotted with ds in the et direction. Dot product of two vectors in the orthogonal directions is 0, which eventually tells me that u12 is nothing but integral 1 to 2 ft times ds. Okay, so this is a fairly powerful statement of the work principle. Okay, this is the work concept or the work principle. We have not come to the theorem yet. Okay, so I'll specify that. But from Newton's law, I know that force is mass times acceleration. Tangential acceleration is mass times dv by dt, or rate of change of velocity. Okay, which I can further write as the following. Okay, so this is m times dv by ds by dt, right, by making use of the chain rule. So which tells me that this ft person and ds by dt is nothing but v, so I can write this as m times v times dv by ds, which means if I take this and substitute this, okay, which means then I get u12 integral 1 to 2, instead of ft ds, it's going to be m times v times dv by ds times ds, and obviously you can see that I can cancel off this and that, and this leaves me with something really nice, which tells me u12 is equal to integral 1 to 2 mv dv, which can be integrated easily. Okay, which tells me that u12 is going to be, if I do the integration here, so this is mv square by 2 And so this is going to be from position 1 to position 2. So the limits will be the velocity at position 1, velocity at position 2. Now this is going to be half m v2 square minus half m v1 square. Okay, so this is something that you can very easily see. Now we're going to define a quantity. Okay, we're going to define a quantity, which I think you have an idea of what we're going to define, right? We're going to define kinetic energy. Okay, kinetic energy at some position is Ke is equal to half mv square, which means that kinetic energy at position 1 is half mv1 square, kinetic energy at position 2 is half mv2 square. Kinetic energy is always a positive quantity. Okay, that's something that you can see very easily from here, which essentially tells me that U12 is going to be Ke2 minus Ke1, where Ke2 is half mv2 square, Ke meaning kinetic energy, Ke1 is half mv1 square. Okay, so let me underline certain things. So I'm defining kinetic energy as Ke, and here is the foundational equation that is called as the work energy theorem, the net work done by the particle. Okay, so this is called as the work energy theorem. Okay, which is this statement here, U12 is Ke2 minus Ke1, and the meaning of this statement is the following. Okay, the net work done by the external forces, by the net external forces on the particle, okay, is equal to the change, this can be called as, delta Ke, equal to the change in the kinetic energy of the particle as it moves between positions. Okay, so this is the work energy theorem. This is the foundational statement of in a sense something that we're going to be making use of in solving several problems. So this is an important thing that you have to understand, where U12 is the work done by the external force on the particle. Okay, so here I want to mention this. U12 is the net work done by all the external forces. So let's say let me backtrack, by all the external forces on the particle. Okay, so this is the work done by the net external force. Okay, so by all the external forces on the particle. Okay, that is a very important statement. All right, so this is the work energy theorem. What are we going to do with this one? Okay, I'm going to do a couple of things. First thing is the following. Okay, first thing, I will obtain the work done by the force of gravity. Okay, so work done by the force of gravity, okay, which I'm going to call as U12G. Okay, let me underline this. Okay, let me make sure that the G is not hidden underneath here. Okay, so this is U12G, and to do this, let me consider a particle that is traveling along some arbitrary path. Okay, so look at this. I'm considering only the effect of gravity. Okay, so this is the x-axis. Maybe my x-axis has to be perfectly horizontal, right? This is the x-axis, and then this is the y-axis here. Okay, the unit vector along the x-axis is little I, as you know, and then unit vector along the y-axis is going to be little j, and here is the particle which is traveling from some point here to some other point there. Okay, now this is position 1 of the particle, this is position 2 of the particle, this is the particle at some arbitrary position. Okay, so at position 1 the height of this particle from the x-axis is let me call this as height y1. At position 2 the height of this from the x-axis, I'm going to call it as a height y2. Okay, let me make sure it extends here. So this is the height y2. Okay, and then so at some arbitrary point in time, the height of the particle is going to be some height y. Okay, and so here is the particle at some arbitrary point in time. This is position 1, this is position 2. Okay, what is the force acting on this? I'm considering only the force of gravity for the time being, so I'm going to say okay, the force of gravity is acting vertically down. Okay, as you can see. Okay, so this is Fg. Okay, now I'm going to write Fg as a vector. Okay, so Fg, if I write it as a vector, is 0I minus mg in the j direction, right? And then the displacement vector of the particle at any point in time can be written as some displacement in the x direction, some displacement in the y direction. By definition, okay, the net work done u12 by the force of gravity on the particle is going to be from position 1 to position 2 Fg dotted with dr. Okay, which means that u12g is going to be integral from 1 to 2. This is 0I mg in the j dotted with dx in the I, dy in the j direction, as you can see. Right, if I do the dot product, as you can see, 0 times dx is 0, dy times mg is j times j dotted with j is equal to 1. So this is going to give me the following. So u12g is going to be minus integral mg dy, and here I can do from y1 to y2. Okay, and key facts here. First of all, this x-axis that I'm showing you here, this is called as the datum. Okay, so the datum is some kind of a fixed horizontal position from where the heights are always going to be measured. It can be an arbitrary horizontal line. It can be a line above or it can be a line below, but if you're starting off with the datum, it has to be consistent throughout the problem that you're solving. Okay, mg dy is fairly easy to find out. Okay, so this means that u12g is going to be minus mg y2 mg y1. Okay, so this is typically how it looks like. Okay, or u12g is equal to minus mg y2 plus mg y1, which tells me the following, which tells me that at some height y, okay, what is the work done due to gravity? So ug is going to be actually minus mg times y. Okay, which means that u12g can be written as ug at position 2 minus ug at position 1. Work done by the force of gravity at position 2 minus the work done by the force of gravity at position 1. The difference between that is the net work done as I go from position 1 to position 2. Okay, so this is something that you can see very well here. So which tells me eventually that okay, u12g is equal to minus mg y2 plus mg y1. Okay, so I'm going to underline some of these things. So at some height, this is the work done by the force of gravity. Okay, and this is the net work done by the force of gravity. So maybe let us rewrite these things again, because these are going to come back for us again. So u12g, let me put my parenthesis properly, u12g, which is ug2 ug1 and which is minus mg y2 minus mg y1, okay, is, so here u1 to g is the work done by the force of gravity on the particle. Okay, so that is important to understand. Okay, so and I want to underline these things as well. So this is one thing that we will come back to again, which is going to help us simplify things. And then this is work done by the force of gravity on the particle. The second thing I want to consider is the force work done by the spring force. Okay, so let me do that very quickly. So I come back, I call this as A, so let me call this as B. Okay, so this is work done by the force due to a spring. Okay, this I'm going to call as U12 because of spring S. Okay, the spring semester is a little while away. All right. Okay, so I'm going to consider a particle attached to a spring. Okay, so here is the situation that I'm going to be drawing. So I'm going to draw three figures, which you will see in a minute. This is my spring here. Okay, so here is the particle. This is the initial position or equilibrium position of the particle. Position of the particle. Okay, and in the equilibrium position, the length of the spring is called as the unstretched length or the length L naught. Okay, so here this length here I'm going to call it as L naught. Okay, L naught is called as the unstretched length of the spring. Now I'm going to consider at position 1 and position 2. Okay, so what happens is that as I apply some force on this particle, perhaps the particle is going to move. Okay, so maybe I give it a certain displacement. Okay, so at position 1, here is the situation. Okay, at position 1, maybe I'm going to be displaced by a little bit. I wanted a spring there. Okay, it does not turn out to be a spring, it turns out to be something else. Okay, so this is, I'm going to say, is at position 1, okay, where the particle is here, and the length is going to be a length L1, let's say. Okay, so this is so equilibrium, which let me bring it closer here. So this is the equilibrium position, then this is position 1, and then position 2, I take the same thing and then I stretch it by a little more. Okay, so here is position 2, so let me redraw the same thing, but then it is stretched a little more. Okay, so which means that I'm going to go a little longer on the way the spring is stretched, so probably a good stretch here. All right, so this is going to be the length L2. Okay, and let me say this is length L2, this is position 2, and the thing that I want to mention here is this. Okay, the displacement of the spring of the particle from the initial position with respect to position 1 and position 2, I'm going to draw a straight line. Let me bring this guy and align it here. So look at this, I'm going to draw a straight line starting from right there. Okay, and I'm going to make it as a dotted line. Okay, and then I'm going to draw one more line here. I need to first select a line. Okay, and then I'm going to draw one more line here. Okay, so these are also going to be dotted lines for me. Okay, that's one line here, then this is another line right here. Okay, so what I'm going to say is that this length here is going to be the displacement of the spring as it goes from the initial position to position 1. Here is the displacement of the spring as it goes from initial position to position 2. I'm going to call this length as x1. I'm going to call this length as x2. Okay, I hope this is clear to everybody. So x1 and x2 are the deflections of the spring at position 1 and position 2. Okay, so this is position 1, need to be straight. This is position 1, this is position 2, and then this is the equilibrium position of the particle. Okay, and this is the unstretched length of the spring, is the length of the spring when it is undeflected. Okay, or the undeflected length of the spring. So x1 and x2 are the deflection of the spring from its unstretched length at positions 1 and 2 respectively. Okay, we are going to go somewhere with this one. Okay, so if I draw the free body diagram, okay, and I know from the spring law, so from basic spring law or Hooke's law, okay, from Hooke's law we know that the force of the spring Fs is proportional to the displacement of the spring. So x is the displacement or the deflection of the spring, so this is the net deflection of the spring from the equilibrium position. So deflection or displacement at some position. Okay, this is measured with respect to the equilibrium position. Okay, so here x is measured relative to the equilibrium position. Okay, so this is important. And so what I'm going to do is I'm going to draw the free body diagram of the particle. So at this position, so let me maybe bring it to the next page here. Okay, so at some position, okay, let me maybe do a couple of things. Let me copy my figure from here. This is the unstretched length of the spring. Okay, I'm going to copy that and I'm going to bring that here. Okay, this is the equilibrium position. I can maybe reduce the size of this guy, and then I'm going to draw the same thing at some arbitrary position. Okay, please bear with me while I do that. Okay, so this is the position at some point in time, so which means that this distance that I'm looking at here is the distance x that I'm measuring, which is the deflection of the spring or the displacement from the equilibrium position. Now I'm going to draw the free body diagram of the spring. Okay, so this is at some position here. Okay, with respect to the spring, and if you want, you can call this entire thing as the spring length here. Okay, so this length starting from here all the way to there is the spring length. Okay, so this is the length L at this particular position. So what am I going to do with this? I draw the free body diagram of the particle. Okay, look at that. If I draw the free body diagram of the particle, the direction of the displacement of the particle is this way. Okay, so this is the direction of displacement. But then what is the spring trying to do? The spring is trying to pull the particle back to its equilibrium position, right? So this is the direction of the spring force. So the key thing here is that the direction of Fs is opposite to the direction of displacement. Okay, which means that if I now try to define the force with respect to the unit vector, so let's say that this is the positive x-axis, if you'd like to call it this way, then I have Fs is equal to minus k times x in the I direction, dr, because it's being deflected only in the x direction, is dx in the I direction. Okay, which means that u1 to s is going to be integral from 1 to 2 bear with me, minus kx in the I direction dotted with dx in the I direction. I dot I is equal to 1, which tells me that okay, u1 to s is minus integral 1 to 2 kx dx, or this is going to give me the following: u1 2 is going to be minus half kx2 square minus half kx1 square. Okay, that is typically how we are writing it out. Or I can say u12s is equal to minus half kx2 square minus half kx1 square, or u12s is equal to us at position 2 minus us at position 1. Okay, so two things that I want to underline here, and then I want to continue with the next segment of my concept talk here. Okay, I want to finish this off hopefully in one segment, but we'll see. Okay, so here I got to get back to my pen. All right, so here u12s is the force exerted by the spring on the particle. Okay, so these are the two things that we have so far. All right, and so which means that us at any position, so at any position where the displacement is x of displacement x, then us is going to be minus half kx square. Okay, so that is something that you want to keep in mind. Okay, this might be a little different from what you might have seen earlier probably. Okay, now I'm going to define a couple of new terms. Okay, I'm going to define potential energy, okay, due to gravity. Okay, so this is now going to be potential energy due to gravity, okay, or PEG. Okay, potential energy due to gravity is going to be defined as the following. Potential energy due to gravity is the work done by the particle against the force of gravity. Okay, so this is something that you got to keep in mind. This is the work done by the particle, okay, against the force of gravity. Okay, which I guess that did not come out to be a straight line. This is sometimes, pretty much miserable when you don't get it to be straight. All right, so this tells me that, if I go back to our previous situation, so this tells me that PE due to G is minus UG. Okay, this is because of the fact that U suffix G is the work done by the force of gravity against the particle. Once again, not a straight line, bear with me. So this essentially tells me the following. Okay, so the work done by the particle against gravity is equal to the negative of the work done by the force of gravity on the particle. Okay, so that is exactly what this is telling me, and then this term is going to be PEG. This is equal to negative of UG. Okay, this entire term is U suffix G. Okay, so this is one definition, okay, that I'm going to have, potential energy due to gravity here. Okay, and then I'm going to say, okay, what is potential energy due to spring? That is another definition that I'm going to have. Okay, so next one is potential energy due to springs. I'm going to call it as PE, potential energy, S for spring. Okay, so potential energy due to spring, exactly the same way that I have defined the potential energy due to gravity. Okay, look at this. Now PES is the work done by the particle against the spring force. Okay, if I take a particle and the spring force is trying to pull the particle back, the particle has to do work against this force. Okay, which means that this is a negative of the work done by the spring force. Okay, so which tells me that PES is going to be minus US. Okay, this is also something that we have seen. Okay, so I want to underline this. Okay, so PES is equal to minus US, and exactly the same thing. I'm going to do a very quick copy paste. Okay, so bear with me for a minute. I'm going to, because I'm getting a little lazy with age, and I'm going to do a quick copy paste. Okay, so this is I'm going to cut that off by the force of the spring on the particle. This is really nice, isn't it? I can do all these kinds of shady stuff with this software here. So work done by the particle, I think I missed, yeah, by the particle against the spring. Okay, this is the work done by the force of the spring against on the particle. Okay, so which means that, you know, in this situation this is going to be called PES, and then this is going to be called minus U of S. Okay, so keep these two things in mind. Okay, and then so I'm going to have my collection of things taking place. So far what we have is the following. Okay, so far we have the following. Okay, so let me go back and collect all of the things that I have from before. So I start off with even before this I had the work energy theorem, right? So I'm going to go and bring this particular guy here. Okay, so I'm going to copy that, and then I'm going to bring that here. Okay, bear with me while you get a little dizzy as I keep moving up and down. Okay, then I have here two things, U12 G. So I have this guy here which I'm going to copy, and then I'm going to bring that and write it down here. Okay, so this is one. Then I'm going to do the same thing for the spring, which I had written somewhere here. Okay, so I'm going to copy that, and then I'm going to bring that down here. Then I'm going to bring two more statements, which, as you can imagine, is going to be this guy here first of all. Okay, that's one thing. And then the last one is all from here. Okay, so I'm going to copy that, and I'm going to paste that, and let me make sure I'm writing it all in the same form. Okay, so this is minus U suffix G. So I have A, B, C, D, and E. Now comes the clincher. Now, with all these terms defined, okay, U12 is the total work done, U12 is the work done by the force of gravity, U12 is the work done by the force of the spring, PE is potential energy, KE is kinetic energy. I can now say, okay, so now U12, which is the total work done by the net force on the particle. Okay, we will split this. U12 into three pieces. Okay, so U12 total is U12 due to gravity, U12 due to spring, U12 others, which I'm going to call as U12 others. Okay, so what is U12G? Is the net work done by gravity on the particle. My writing is all over the place. Okay, U12 spring is the net work done by any spring forces if they are present, by spring forces on the particle. Okay, that is supposed to be an L. Okay, and then U12 others is the net work done by all non-gravity and non-spring forces. On the particle. Okay, so this essentially includes work done by constant forces or varying forces, by constant applied forces, and also the force of friction, and by the force of friction. Okay, so this is number 1, number 2, and number 3. So I go back to my work energy theorem, which implies that U1 to G, U1 to S, and then U1 to others is equal to KE2 minus KE1. Now here is what I'm going to do. But we know U1 to G is, what is U1 to G? I have it as UG2 minus UG1, right? So this is going to be UG2 minus UG1, which means that this is going to be, instead of UG2, I'm going to say this is minus PE G2 minus PE G1. And I'm substituting the potential energy instead of writing it in terms of the work done. This is U spring 2, U spring 1. This is going to be minus PE spring 2 minus PE spring 1, which implies that U1 to G, I can write it as the following. Negative becomes a positive, so this is PE G1 minus PE G2. Potential energy, PE is potential energy. U1 to spring is PE S1, PE S2. And so if I do the substitutions, if I substitute into the work energy theorem, I have the following. Okay, so instead of U1 to G, I have PE G1 minus PE G2 plus PE S1, my comma and 1 look the same. That is what I recognized here too. Okay, this is PE G1, PE S1 minus PE S2 plus U1 to others is equal to KE2 minus KE1, or I'm going to rearrange this in a much nicer way, and you're going to see something really nice happening. So U1 to others there was a movie called The Others. I don't know if you've seen it. It was kind of scary when I was a young kid. I don't know, I wasn't that young at that time, but it was still pretty scary. Alright, so U1 to others plus PE G1, once again my commas are, and PE S1 is equal to, and I'm going to bring the KE onto this side as well, so plus KE1 is equal to PE G2 PE S2 plus KE2. This is the most convenient form of the work energy principle. Okay, so this is the most convenient form of the work energy theorem. Okay, and here PEG is equal to minus UG, which implies that PEG at some position, is just going to be mg times y. Okay, which essentially implies that PEG1 is mg y1, depending on where we are applying it. Okay, PEG2 is equal to mg y2, etc. okay, depending on the datum, of course. Okay, so I want to make a caveat here. This is dependent on the datum. Okay, which you will see in some problems that we're going to be solving after this. Okay, and then we also can say, okay, PES, which is minus US, which implies that PES is equal to half kx square, which implies that PES1, I guess PES comma 1 is equal to half kx1 square. PES comma 2 is half kx2 square. Okay, this is not dependent on the datum, this is always true. Okay, so this is always true. Okay, so a couple of caveats here. One is the way you define the gravitational potential energy depends on the datum. It could be positive or negative depending on how you're defining the datum. This is always true. Okay, but in general the statement that is always true is the following. So overall, okay, overall you can say that U1 to others, so work energy theorem, the convenient form is U1 to others plus KE1 plus PE gravity 1 PE spring at position 1 is equal to KE2 plus PE gravity at 2 PE spring 2. Okay, this is the most general form of the work energy principle, okay, or the work energy theorem. In a special case, okay, so if I look at a special case, that special doesn't look very special. Okay, if I look at a special case, if U1 to others is equal to 0 in the absence of friction and any other applied forces, okay, then what will happen? If that is the case, then I get KE1 PEG1, and then I'm going to have PES1 is equal to KE2 PEG2 PES2, or if I rearrange it, okay, this can essentially be written as PEG2, minus PEG1 PES2 S1 is equal to KE2 minus KE1, or you can say that this entire thing is delta PE is equal to this entire thing, which you can call as delta KE. Okay, so the change in potential energy is the same as the change in the kinetic energy. This is in the absence. Very important thing is this is only purely only in the absence of friction and any other applied external force. Okay, so this is just a special case. Okay, this is just a special case. This is not the equation you want to remember. The equation that you want to remember is right up here, this big guy here. Okay, so this is the main equation. Okay, so this is the main equation. So main equation is shown down here. Okay, this is just a special case that I can look at. Okay, this is only in the absence of any friction or any applied forces, which is a very common form of energy conservation. Okay, so this is a form of energy conservation. Okay, but this is only in the case of this, where you have an absence of friction and any other applied force. If you have friction, or if you have any other applied force, even in the absence of friction, if you have an applied force, this is not going to hold true. Okay, so include that. Okay, so this is in the absence of friction and any other applied external force. All right, so this was a long concept talk. My battery is running low, as you can see, but I hope this has been useful. You can come back to this again and again as you require. Okay, thank you very much, and take care of yourselves. Bye bye.